Charney. I don't know if you know, Jules Charney is kind of like the Superman of meteorology. There's almost nothing there's almost nothing he didn't know about. There's a lot of this material that's in this paper here it's been reinvented or rediscovered over the last 30 years or so. I won't cover all the material in this paper, even though it's a note, but it's full of important. I think it's a really important paper. I won't cover all of it. There's some stuff at the end which I'll point you towards, which I think is, if you're really serious about understanding the tropics, you're looking to look at. So, why are the tropics different from the mid-latitudes? And this is I just took this picture this morning. This is this morning's analysis over Southeast Asia and Australia, and it's MSLP. And here's the principal point here. If we look in the tropics, as Ailey told us, look in the tropics, the pressure gradients are weak or almost non-existent. And we've got a depression here, but the pressure gradients are very weak, whereas in the mid-latitudes, the pressure gradients are relatively strong. You can see this is our little east coast low that's affecting us at the moment. But in the tropics, essentially flat. And the same is true of the temperature as well, and any other thermodynamic variable you'd like to name. They're flat. Whereas in the mid-latitudes, there are large gradients. Now, why is that? Well, it's got something to do with the rotation of the Earth. The Coriolis parameter is small in the tropics, that's true, we'll see why. It's also got something to do with what the energy balance, in that there's an excess of, so there's more incoming short wave in the tropics compared to the outgoing long wave. That's part of the story as well, but really, how does it all fit together? All right, Newton's second law. Newton's second law, F equals ma. The mass times the acceleration is equal to the sum of the forces acting on the fluid, on the atmosphere. Newton's second law is, of course, one of the fundamental governing equations of the atmosphere. So up the top here, this is the horizontal component of it. And what does this say? The acceleration, or what's the acceleration? If I take a pass from the atmosphere, here it is at some position in space and time, and it moves over here some time later. You take the difference, divide by delta t, you take the limit as delta t goes to 0, that's acceleration. The acceleration following fluid parcels as measured by someone standing on the Earth, which is rotating. But of course, when we're rotating Earth, the acceleration has another term to it, and this is the Coriolis acceleration. K is unit vector, points upwards, and K cross, as you take your handy right-hand rule, K is pointing upwards, K cross U, U is pointing that way, K is pointing up, K cross is a vector which is horizontal and perpendicular to both the vertical and the velocity vector. And the right-hand side is the pressure gradient. So this is the net force on the parcel. I'm forgetting about friction here, but the net force is given by this. Sometimes the density is written out the front here. I've slipped it inside the grad operator. Let's not worry about that today. The vertical component of Newton's second law, we often make an approximation, and we say that we'll just neglect the acceleration, we'll just think about the balance of forces. The pressure gradient force balances the force per unit mass due to gravity. Minus 1 over rho dp dz balances gravity. So this is hydrostatic balance, or the vertical component of Newton's second law, and here's the sort of horizontal part of it. We're going to have a look at these some balances. Let me say, in this lecture, it's all about back of the envelope calculations. I'm going to do rough calculations, scaling analysis, back of the envelope calculations. I wish I had an envelope here. I could just do the calculations rather than This is unbelievable. It's an engineering lecture here. There's no whiteboard or anything. There you go. And it's all going to be about back of the envelope calculations, and we'll try and understand why the tropics is so different from the latitudes. Just without too much reference to observations, just think about why it has to be like this. I'll refer to the observations a little bit later on, but not much actually. We're going to do a scale analysis, and what that means is we're going to estimate how big are terms. So in Newton's second law, acceleration, Coriolis, pressure gradient term, how big are these terms? Well, for example, this one here is the Coriolis term. F is the Coriolis parameter. 2 times the rotation rate of the Earth times the sine of the latitude. F goes to 0 at the equator, It's maximum at the poles. It's maximum positive at the North Pole, maximum negative at the South Pole. It has value F. U, how big is that? Well, it's about big U. I'm not saying it's exactly big U, okay? It's roughly big U. It's big, what's big U? That might be a metre per second. It's not 100 metres per second, it's not a millimetre per second. It's a scale. It's telling you roughly how big something is. So the Coriolis term is about F times U. The acceleration is U squared on L, where U is the scale of the velocity and L is the length scale. What's that saying? That's saying if U is the scale for the velocity, if the velocity is about big U, what would we use for time? This should be a velocity divided by a time. Well, the time is how long does it take for a parcel of air to move a distance L if it moves at speed U? How long is that? Well, it's L divided by. And so we get U squared on L as that's the scale for the acceleration. The pressure gradient, delta P. We go back to our pressure chart. Delta P is how much is the pressure change in the horizontal over a distance L. So however big L is, I measure the pressure, that's delta P. And rho is just rho. So these are estimates for how large those three terms are. And for the people, if you've done any dynamical meteorology or fluid mechanics, you'll know that fluid dynamicists, meteorologists love the one-dimensional numbers. They like to form numbers that tell you something about the dynamics of the flow. For example, in fluid mechanics, you would have come across the Reynolds number, which tells you about the importance of the friction, viscosity. And one of the most important numbers in meteorology is the Rossby number. Another one of these giants in meteorology, like Charney, Rossby. The Rossby number tells us how important rotation is. It's the ratio of this Coriolis term, well, it's actually the ratio of the acceleration to the Coriolis term. The acceleration to the Coriolis term, one divided by the other. U squared on L divided by F over L, F times U is U over FL. This symbol here means, it does not mean approximately equal to. This symbol means of order, goes like. It's of order U over FL. This has a special name, the Rossby number. When the Rossby number is small, that would be when L is large or U is small or F is important. Small Rossby numbers mean the rotation of UF is important. In the latitudes are characterised by Rossby numbers which are small b compared to 1. The tropics, on the whole, Rossby numbers are not small, except at the very large scales of the tropics. So that's an important number. We're going to use that a lot. So let's get cracking and see how we can use some of these ideas. There's the Newton's second law, there's the scaling. Now, if the Rossby number is small, what does that mean? The Rossby number being small means that the Coriolis term is important relative to the acceleration. That's important relative to that. In other words, what does that mean? If that means we take the acceleration, we think it's small, get rid of it, this balances this. Or in other words, delta P would be divided by rho times L, would be about the same size as F times U. Or rearranging that, delta P goes like rho F U L. That tells us how big the pressure has to be. If I tell you how large, I go back to my weather chart and I look at this and I go, well, you know, the length scale here, well, it's about 2,000 kilometres, and U is about a metre per second, and rho is about 1 kilogram per metre squared. That tells me how big delta P would have to be, the pressure gradient would have to be, or the change in pressure would have to be. And that's what we get for small Rossby numbers. But what if the Rossby number were 1, and that's more applicable to the tropics? What if the Rossby number was 1? What that says to us is that everything's important. That this is as important as this, is as important as this. So delta P could be written as balancing FU, or we could say delta P divided by rho U balances U squared on L. either is equally valid because every term is important. So in other words, delta P is rho FUL or rho U squared. Because the Rossby number is 1. So we can take it out here. So this is the value of the Rossby number that's most applicable to the extratropics. This I'm asserting is a number that's more applicable to the tropics. The reason for saying that also, by the way, is all things being equal, if U and L were the same, and F, we go towards the tropics, what happens? F gets smaller. In fact, F goes to 0 at the equator. So as F gets smaller in the denominator, the Rossby number gets larger. The typical number of F in the tropics is 10 to the minus 5 inverse seconds. The typical number in the mid-latitudes is 10 to the minus 4 inverse seconds. Factor of 10 difference. Okay, and this is a restatement of just what I said. In the mid-latitudes, well, here's Newton's second law, but as the Rossby number gets smaller and smaller and smaller, the acceleration gets smaller and smaller, and we have a balance between the Coriolis and pressure gradient, and there it is. And if we rearrange this, we get that U, the wind, is equal to 1 over F A across the pressure gradient. That is the definition of the geostrophic wind. That is the wind, and the Rossby number goes to 0. Now, that is not a very good approximation in the tropics, and probably everybody here knows that. Geostrophic balance is not a good approximation in the tropics because the Rossby number is not small. What is a good approximation in the tropics? Let's just call it out. All right. Now, this is what Charney did, and I think this is pretty important. These next few slides. Let's first of all define something called the pressure scale height. So if I take d by dt of z, P is the pressure. I put a subscript at 0 on it just to mean it's the basis, average over time, some sort of representative reference value of the pressure. The sort of profiles A shows. So I differentiate with respect to z, and I divide through by 1 over P. That's called the scale, minus that's called the scale height. It's telling us something about how fast is the pressure changing. What is the fractional change in pressure? So it gives us a height scale. How quick, and we know for an isothermal atmosphere, the pressure will decrease exponentially, and that the rate of that constant may decrease. So exponential e to the minus divided by h is that. If we use hydrostatic balance, if P by dz, what's that? Minus rho times G, then the scale height is the pressure divided by gravity divided by the density. Now, if the Rossby, so we're just looking at the scaling for mid-latitudes at the moment, and then we'll do the scaling for the tropics and see how it's different. If the Rossby number is small, then we saw that the Coriolis term balances the pressure gradient term, and that means that delta P goes like FUL, pressure balancing Coriolis. And there it is. So delta P divided by P is delta P divided by, what's P? P is HS rho times G. There it is in the numerator. Delta P, what is that? Rho FUL. Do some algebra. And that works out to be big F squared divided by R naught. R naught is the Rossby number, and F is the proof number. It's a new non-dimensional number. There are dozens of non-dimensional numbers. There's a new one, and there are two principal non-dimensional numbers that we're going to use in this lecture. The Rossby number, which talks something about the rotation rate, and the proof number. Now, the proof number is defined as U divided by the square root of G times H. The proof number is a bit like, the proof number for the atmosphere is a bit like the Mach number in compressible flow. It's telling us about the ratio of a velocity to another kind of velocity. The thermodynamics here recognise this. Wave speed on a shallow layer of fluid, long wave speed is root GH. So it's two kinds of velocities. This is a velocity that comes out of the gravity and the height scale of the pressure plate scale. and here's the actual velocity we're measuring. But here's the really important thing, that the fractional change in the pressure goes like the Froude number squared divided by a Rossby number. Let's keep that in the back of our mind. That's a really important relationship. Let's do the same thing for the tropics now. In the tropics, and here's the big difference, that the Rossby number is 1. Remember, what does that mean? It means that every one of these terms are important. It also means that when we go to ask how big is the pressure change in the horizontal, well, it's rho FUL or it's rho U squared. We don't care. We can take either. So let's do that. So let's do that. Let's take delta P divided by P naught. And if we use rho FUL, that's identical to what we did in the mid-latitudes. We get F squared on rho 0. If we take delta P divided by rho naught and use this as our scale for delta P, P U squared, we get an F squared. But these two expressions are identical because here, in doing this, we've assumed that the Rossby number is 1. So F squared over 1 is the same as F squared. So this expression, F squared over rho naught, the Froude number squared divided by the Rossby number, is true in the latitudes and it's true in the tropics. It's true for small Rossby number, it's true for Rossby number of 1. So, what's more, and Johnny shows this, if we did the same analysis for temperature or density or any other thermodynamic variable, we get the same relationship. That the fractional change in whatever thermodynamic variable you're interested in, whether it be pressure or temperature or potential temperature or density, they all go like F squared on R naught, and it doesn't matter whether the Rossby number is small, it doesn't matter whether the Rossby number is 1, that's still a relationship. So here's a fundamental relationship that tells us about the fractional changes in the pressure, the density, the potential temperature. It's telling us how big the horizontal changes have to be. So you can see we're getting towards why are the gradients in pressure and temperature and everything else small in the tropics? And why are they, in a relative sense, large in the extratropics? Let's put some numbers to this. Right, so we've done some theory. Let's put some numbers to it and see how big these things really are. So let's take G to be 10. That's good enough for us. It's in a factor of the envelope calculation. HS, the scale height of the pressure. About 10 things. About the depth of the case. It's not exactly that. It's good enough for us. About 10. U, maybe about 10. F, we're in the mid-latitudes, 10 to the minus 4. That's a typical mid-latitude number. 10 to the minus 4 inverse seconds. Rossby number would be 0.1. And the Froude number, if I went back to the definition and popped some numbers in there, I'd get 10 to the minus 3, the Froude number squared. Take those numbers, put them into this relationship here. Delta P over P, delta density divided by density, delta potential temperature divided by potential temperature. It's all about 10 to the minus 2. So they're small. The perturbations in temperature are small in the latitudes. What's this say to us? If a typical weather chart with highs and lows, well, we have a typical weather chart, don't we? Let's go back to it. Here's a typical weather chart. If I were to say, well, what's the length scale here? Let's call it 2,000 kilometres. I was to measure how big is the temperature change across that 2,000 kilometres. I get, well, it's about 1/100th of whatever we're talking about. So if we're talking about pressure, it's about 1/100th of that. So if we're talking about 1,000 millibars, the pressure change might be 10. If we're talking about temperature, 300 degrees, the temperature change might be 3. That's a typical sort of number. Let's do the same for the tropics now. We have this relationship between these fractional changes in our thermodynamic variables, F squared over R naught. The principal difference here is this. F is now an order of magnitude smaller. The Rossby number is order 1. And now the relationship between these variables is 10 to the minus 3. instead of delta, whatever your favourite thermodynamic quantity is divided by that thermodynamic quantity, instead of being 100, it's now 1,000. It's a tenth of what it is in the tropics. Let's go back to our weather chart, today's weather chart. In the tropics, the pressure gradients are about a tenth of what they are in the mid-latitudes. The temperature gradients are about a tenth of what they are in the mid-latitudes. The density gradients are about a tenth of what they are in the mid-latitudes. So notice what we've done. I've not really appealed to observations much at all. I've just simply said, if the Coriolis parameter is a tenth in the tropics of what it is in the mid-latitudes, what are the consequences? And the consequences are that in the tropics, thermodynamic fluctuations are order of magnitude smaller than the mid-latitudes. So just sort of, without actually going and looking at the tropics, we've come to this conclusion. So rotation imposes constraints on how the pressure field and the mass will adjust. In the tropics, the strain is less. In other words, it's sloppier. The pressure field is going to be flatter. All right, let's use some of this information now in the other really important law for meteorologists and climate scientists, the first law of thermodynamics. First law of thermodynamics is based on conservation of energy. The most useful form of the first law, the most useful form, but one of the most common forms of the first law in meteorology is this. d by dt of the log of the potential temperature is the heating rate divided by the specific heating constant pressure divided by the temperature. If you take the Cp the other side, Cp times log of theta, that's actually the specific energy. Another way of thinking about this is if there's no heating, so the right-hand side is 0, then d by dt of log of theta is 1 over theta d theta by dt equals 0. In other words, d by dt of theta equals 0. In other words, theta is conserved. So for adiabatic motion, theta is conserved. Potential temperature is conserved. That's one of the reasons we use it. We take the material derivative and expand it. Partial derivative with respect to time. Horizontal advection, vertical advection equals the heating rate. That's our first law. Potential temperature, log potential temperature, if we like, satisfies that. Let's see what the implications are of our scale for this. After all, we've said that the change in the potential temperature divided by a potential temperature is so like x squared on r. Now, what I'm going to do at this point is I'm going to say, let's suppose that diabatic heating is not important. Ailey told you it was important in the topics, and there's no doubt it is. But I'm going to follow the approach of saying, suppose it's not, see what happens. What we're going to do is get a kind of contradiction. Reductio ad absurdum for the mathematicians here. We're going to suppose it's can be neglected and show that is a bad idea. Right? And then I'm going to say, let's put it back in, and suppose it's radiative cooling, or suppose it's convection. What do we get? And let's see where that takes us. So here's step one. Let's suppose that the diabatic heating can be neglected. And actually, that's a pretty good approximation in latitudes. Actually, in latitudes, we don't really need to use diabatic heating to understand how the world works. In the tropics, it turns out we really do. There's no way around this. So here's the equation from the previous, this one here. Let's make the right-hand side 0, and there it is. The rate of change of the log of potential temperature, the advection of potential temperature, the horizontal advection, and here's the vertical advection of potential temperature. And let's do a scale analysis again, another back of the envelope calculation. d by dt, or d by the anything of log, if you differentiate log, what do you get? 1 divided by. So the derivative of log of theta is 1 over theta. So the derivative of log of theta with respect to t is 1 over theta d theta dt. So the derivative of log gives us a change in theta divided by theta. And here's our time scale, or alternatively, think about it as a u. And what's a grad? A grad is a 1 over a length scale. It's a d by dx, d by dy, so it's a 1 over a length scale. So these two terms here scale like u divided by L, delta theta divided by theta. And this term, the vertical advection of potential temperature, scales like whatever W is, d theta by dz divided by theta. D theta by dz d theta divided by theta, you probably recognise that already. G times that is the vice frequency. G over theta naught d theta dz times vice frequency. There it is. D theta divided by theta, just spent 15 minutes on that. F squared on R. Over Rossby number. There it is there. We rearrange this, and after a few lines of algebra, we end up with this. And it says that the vertical velocity divided by the height, the W divided by height, goes like a U divided by an L, 1 over Rossby number, and here's another non-dimensional number, the Richardson number. N squared, H squared over U is called the Richardson number. We don't need it much in today's subject. That's just what it is. Let's put some numbers in, see how big things are. So there's our scaling. This is how big W is. Typical numbers for synoptic systems, 10 metres per second for U, 1,000 kilometres for length scale, height scale of 10 kilometres, N is about 10 to the minus 2 inverse seconds. The Richardson number is about 100. No reason we should know that, but it is. You put all those numbers in here, and you find that the vertical motion is 10 to the minus 3, 1,000th over the Rossby number. So in the tropics, the Rossby number is like 1. So that means the vertical motion is like 10 to the minus 3. It's like a millimetre per second. That's tiny. That's unrealistic. In the mid-latitude, on the other hand, W is 10 to the minus 3 over the Rossby number. The Rossby number is 0.1. So that gives us about a centimetre per second, which is not too bad. So what do we take from this? We take away that in the mid-latitudes, the adiabatic approximation is not so bad. The vertical motion is basically adiabatic. But the tropics, that's right. It's not enough just a second. That's just right. So that's what I mean. We've come to some kind of, not contradiction, but we've come to a, well, we're at odds with the observations. So what did we do? We used our scaling that said delta theta divided by theta is f squared over r naught. We assumed that the motion was adiabatic, got rid of that, and we found that W goes like 10 to the minus 3 divided by a Rossby number, which gave us a vertical motion of a millimetre per second in the tropics and about a centimetre per second in the extratropics. A millimetre per second in the tropics, wrong. So let's go back and say, well, you know what? These two terms, the advection and the time rate of change of potential temperature, cannot balance the vertical motion times d by dz of the potential temperature. In other words, the horizontal advection cannot balance the vertical advection. And what we have to do is take account of, we have to include the right-hand side, diabatic heating. So let's do that. So now I'm going to do this in 2 steps. If you look at the tropics, and here's just 2 random satellite images. Oh, first of all, I'll just say one other thing. So our conclusion is that unlike the mid-latitudes, we have to include diabatic heating. I told you that. These days, this is not what China called it, but these days, people call this the weak temperature approximation. In other words, temperature gradients in the tropics are not large enough to balance the vertical advection. China knew this in 1963. Now, if you look at the tropics, what do you typically see? You typically see regions where there's no cloud, strong subsidence, strong cooling, and then you'll see other regions where there's active convection. Actually, it's mostly not active convection, really. It's radiative cooling, subsidence, punctuated by regions of active convection. Because in the tropics, about a fifth of the tropics is covered by active convection. About 4/5 is subsidence, clear sky. Now, what we're going to do is look at radiative cooling first of all, and then active convection. So we're going to ask the question, how big would the vertical motion be in this region here? Work it out. And then how big would the vertical motion be over here? Work it out. Radiative cooling, let's look at that to begin with. Now this is a diagram that is very similar to one that Hayden showed. It's the heating budget of the atmosphere. And the idea is this, that if you have 100 units of incoming solar radiation, so don't worry, we've sort of normalised it, don't worry what the actual number is, it's 100 units of it. And how is it split up? Well, you know, your 100 units come in and 8 units of the shortwave radiation is backscattered by the air and 17 is reflected by the cloud, etc. This middle part here is the atmosphere, the bottom bit is the ocean land, this is space. Let me just cut out this middle bit because I'm only really interested in the budget, the heating budget of the atmosphere. Notice also that over here there's sensible heating, which is 7 units, and there's latent heating, which is 24 units. And here I've cut out the atmosphere. There it is there. And these are the arrows of going either into the atmosphere or out of the atmosphere. So in the short wave, the yellow, we've got 100 coming in, we've got 31 going out, and what was that? 31, that's the sum of all these type of things here. How much of it's scattered by the atmosphere and the surface, etc. 46, here it is, yes, surface, etc. The net result, you can go back and look at this. The net result is this. The net radiative cooling of the atmosphere. Sum up all the yellows, sum up all the long waves, which are the reds, and we don't get 0, we get minus 31. That's how much cooling is going on there in the atmosphere. And that's balanced, so that cooling is balanced by this, the sensible heating and the latent heating, which is 7 plus 24, 7 plus 24 plus 31. So the convection is balancing the radiative cooling. Let's look at the radiative cooling bit. Now, this is something you've seen in the literature, I'm sure. So the sun shines on the Earth. The Earth's a sphere, but the Earth intercepts the solar radiation through a disk. And the ratio here of that disk in the area of the sphere is a quarter. So that solar radiation is spread over the sphere. Let's do some back of the envelope calculations. Let's think about the radiative cooling, delta Q. So how much cooling in a particular unit time. So there's cooling as a fraction of the short wave coming in, and the short wave averaged over the whole surface. So it's 0.31, where does the 0.31 come from? As a fraction of what's coming in, there's 100 coming in, and 31 is a fraction of that, 0.31. There it is. There's the quarter, because we're spreading it over the whole sphere. The Earth intercepts through the disk, and spread over the whole sphere, so there's the quarter. And the solar constant is 1360. So that is how much heating there is per unit area per unit time. Now, if you heat the atmosphere by this amount, it'll rather cool the atmosphere by this amount. Then we change the temperature by a certain amount. And that relationship between the heating and the temperature comes from the first law. The first law, delta, the heating equals the specific heat at constant pressure times the mass of that column times the change in the temperature. That's the first law. If we assume that the volume remains constant, then that would be the relationship between the temperature and the heat. And the mass of the column, this is one of these problems that are usually set in your first meteorology class. You go back to, you say, well, show that the mass of the air in some column is equal to the mean surface pressure divided by G. Mean surface pressure, that's a force per unit area, and it's divided by an acceleration force per unit area. F equals ma. The way you get this is you go to you start with the hydrostatic balance and you integrate from the surface to some height. Anyway, the mass of the column is the mean surface pressure divided by G, and there's what it is. At 10 to the 4 kilograms. So what I'm doing here is I'm going to work out delta T. Delta T is delta Q divided by CPMA. The mass of the column is this. The radiative cooling is that. Stick all those numbers into that expression. Delta T equals about a degree per day. The radiative cooling is about just back a little of calculations. About a degree. So what are the implications of radiative cooling of a degree per day? Actually, the radiative cooling is a function of latitude. Paley showed us this. It cools more in the tropics than it does in the extratropics. In fact, delta T is more like about a bit over a degree per day in the tropics. So let's just pump up a little bit. So instead of it being 0.9, let me make it 1.2. Because I know that that's an estimate. That's over the whole globe. That's So let's assume that we're cooling at about 1.2 degrees per day. Now, what did we say? We said that the vertical advection of potential temperature must balance the cooling. So physically, what's this? This is if air rises and adiabatically expands, it cools. So, or if it subsides, the adiabatically is compressed and warms. So the subsidence, or warming due to the subsidence and compression, is going to balance the cooling associated with long-wave radiation. So let's just go back a second and remind ourselves what we're doing here. We're saying we found that these two terms can't balance the heating. But this has to be the balance in the tropics. So we're asking, we've just worked out how much we're cooling. Now we're going to try and work out what the associated W has to be. So physically, subsidence, compression, warming, balancing that cooling. So W, and here's the, and now I've just, I'm calculating this and this, put some numbers to it, put all the numbers in. It turns out to be about 0.5 centimetre per second. So what this says to us is to balance this cooling, there must be subsidence over much of the tropics, and it must be about 0.5 centimetre per second. All right? So there's slow subsidence over much of the tropics. In these regions where you don't see clouds, slow subsidence of about 0.5 centimetre per second. What about over here? What about in the active convection? What's going on there? Well, here. Let's go back to our heating budget. So about 3/4 of the radiative cooling is balanced by latent heating. So 24. Now heating budget, let's go back. That was the latent heat flux. So of 100 coming in, 24 out of 100. That's how big the latent heat flux is. That's about 3/4. And so over in the tropical region, the warming rate has to be about 3/4 of 1.2 degrees per day, which turns out to be 0.9 degrees per day, by coincidence. So if we reach active convection, we expect a Now here, tropical weather systems cover about 20% of the tropics. That's a statement. I'm saying that these active convective regions cover about 20% and these subsidence regions cover about 80%. And that 20% estimate goes way back to the 70s. Meteorologists, very well known meteorologists, who raised the first estimate of that, and subsequently added with more precise measures. That's good. It's about that. About a fifth is in active convection, about 4/5 is power through. Let's go with that, see what we get. So the warming rate is about 5 times this. So where it's active, so this is the rate averaged over the whole of the tropical region. But really, we have to think about where it's warming just within the convective regions. And they cover about 1/5 of the tropical region. So it has to be 5 times higher in those convective regions. And let's do that. 5 times higher, let's call it 4.5 degrees per day. Let's work out what W is, put some numbers in here. It's about 1.5 centimetres per second. And this is an underestimate because where it's convecting, the run Weiser frequency will be smaller than I see here. It'll be more well mixed. So what have we got? What have we got here? What we found is that in regions of radiative cooling, we have subsidence of about 0.5 centimetre per day, and where it's active convection, on average, it's about 1.5 centimetre per day on average. Now that tells us something about the area occupied by convection versus the area occupied by subsidence. If in the convective regions we've got upward motion balancing the heating, and it's about 1.5 centimetres per second average, and in the radiative cooled regions we have subsidence and it's 0.5 centimetre per second, factor of 3 difference. Well, the amount of mass going up, mass flux plus the mass flux up has to be equal to the mass flux down. Otherwise we accumulate mass. So, let's think about the following. The area of down over area up equals W up over W down. That's the other way around, isn't it? So we've got W, no it's not, it's whatever it is, correct. So W down up is about 1.5 centimetres per second, W down, the velocity downwards about 0.5 centimetre per second, so there's a factor of 3 difference. So the area of the downward motion, the subsidence, has to be 3 times the area of the upward motion. And if we look at the fractional area covered by convection, so that would be area up, divided by the total area, which is the area up plus area down, that's 1 plus 1 plus 3, which is a quarter. And that's about what I guessed. I said, oh, the area covered by active convection is about 1/5 of the tropics. We just worked out it's about a quarter. So that's good enough for us. That's about the normalised kind of calculation. So what it's saying to us is that in the tropics, we expect smallish regions of relatively active convection, upward motion, and surrounding regions of relatively slow downward motion, subsidence, but large regions. This also tells us something about the implied rainfall. So these calculations tell us something about how much rain is falling. So we're heating at about 0.9 degrees per day, and the mass of the column we already worked out was this. It's the mean surface pressure divided by gravity, and it's about that. And we've said that in the upward region, the balance of curve is upward motion, latent heating in the clouds. So the heating rate will be the latent heat of condensation times the amount of water that's converted from gas to liquid. And that's equal to Cp Ma delta T, that's what I had back here. Cp ma delta T. So in other words, I'm now being a bit more explicit about where's the heat come from? It comes from the conversion of water in this gas phase to this liquid phase, it's like heating. We're producing water, and if we assume it falls out as rain, how much rain will fall out? Well, we can work that out. We've got all the things we need to work this out. The change in the water is, we know what the Cp is, we know what the mass of the volume is, we know what the change in temperature is, we know what the latent heat condensation is, and therefore, and we also know what the density of water is. So therefore, if we average over all of the tropics, we get about 4 millimetres per day. But if we say, well, you know what, it's not just evenly spread over all the tropics. The rain comes, it falls out of these convective systems, and they cover about a fifth of the tropics. So in these weather systems, it would be more like 5 times that, which is 20 millimetres per day. If you look at the annual average rainfall over the rain rate over the tropics, here it is. And if we think about the tropics as being something like the area between these two lines, or the region between these two lines, these colours are in millimetres per day. And you know, what did we say? We said, well, the average over all the tropics is maybe 4, about 4. And in these weather systems, about 20. Well, the reds here are about 8s, and the greens are about 4s, and the whites are 0. So you know, that's consistent. What I'm saying is the estimate we've got is kind of consistent with what we observe the rain is to be. So let me summarise what we've done today. As I said, this is based mainly on the ideas of Charney. And what we show is that in the tropics, thermodynamic quantities scale this way. Fractional changes in whatever thermodynamic quantity you care about, pressure or temperature, or density, or anything else, goes like Froude number squared divided by Rossby number. Froude number was the ratio of the velocity to some other velocity, that is the long wave speed, root gh. The Rossby number tells you how important rotation was. It's the ratio of the acceleration of the Coriolis acceleration. In the mid-latitudes, this ratio is about 10 to the minus 2, meaning that the fractional changes in thermodynamic quantities are about 1 in 100. In the tropics, it's an order of magnitude smaller again, so there's very little change in the temperature in the tropics, about 1,000th. But then he said, well, let's suppose, let's assume adiabatic motion, let's assume the diabatic effects are unimportant. And then we found that the vertical motion scaled like 10 to the minus 3 divided by a Rossby number. So if we're in the tropics, and the Rossby number was, let's say 1, we've got 10 to the minus 3, which is a millimetre per second. Then in the latitudes, the Rossby number is small, we have about centimetre per second. So it worked out well for the latitudes, but not so well for the tropics. So the conclusion there would be, maybe diabatic effects aren't so important in the latitudes. That's true. You know, we can understand the basic dynamics of the latitude atmosphere without thinking about diabatic processes. We need diabatic processes that understand the details, but not the fundamental dynamics. But we can't get away with this in the tropics. Our conclusion was that we must include diabatic processes in the tropics, even to get the most fundamental understanding of the dynamics of the tropics. And what it also told us is that you can't balance the adiabatic cooling through ascent or the adiabatic warming through subsidence. You can't balance that by horizontal advection. The temperature gradients in the tropics are just too weak. This is called weak temperature approximation. So that meant we're forced to go back and think about what happens if we include diabatic processes, and there are two. There's radiative cooling and there's diabatic heating convection. We did it separately, and we found that the vertical motion in regions of radiative cooling would be about 1.5 centimetres per second average, and in regions of ascent, it would be about 3 times that. So by continuity, that implied that about 3/4 of the tropics had subsidence, and ascent was in about about a quarter of the tropics there was a second. I'd assume it was a fifth, but a fifth, a quarter, for the purposes of this sort of scale, that's close enough. And that also implied that there were rain rates when averaged over all the tropics of maybe several millimetres per day, but when averaged over just the convecting part of the tropics, it's more like 20 millimetres per day. If you go and look at Rossby's Chinese paper, he goes on to do this analysis in the situation. He goes on to show that the large-scale motion in the tropics, and there wasn't a number of the mid-latitudes or the very large scales in the tropics. He goes on to show that the tropical atmosphere is open. There must be either one side of the aloft and the other side of the lower, and a connection is through the diagonal. It also goes over to show that when the Rossby numbers are 1, then the various layers are distant. That would be a good observation for the models of tropical cycling motion. If you're interested in some of those ideas, go back into the Chinese paper. So with that, I think that's just about the end here, so I'll bring that to a close now. Okay, thanks.